Imagine two metallic plates floating in a complete void. At this moment, they are perfectly neutral. There is zero charge and no electric field between them. If we move a single packet of positive charge from the second plate to the first, it takes no mechanical effort. Without an existing field to oppose us, the charge moves freely. But that first move changes the physics of the entire system. The first plate is now slightly positive, meaning it will exert a repulsive force on any subsequent positive charges we attempt to add. Charging a capacitor is a physical struggle against an electrostatic wall that grows taller with every packet of charge we force across the gap. To reach a final charge Q, an external agency like a battery must perform continuous mechanical work, and by the law of conservation, that work must be stored somewhere in the system. This diagram shows the intermediate state. The plates hold partial charges, Q' and negative Q', creating a potential difference, V'. This potential is the ratio of charge to the system's capacitance, C, which measures charge capacity per volt. Moving the very next infinitesimal charge, delta Q', across this gap requires a tiny bit of work, delta W, which is the product of that potential and the charge element. Because the potential V' increases as the total charge Q' grows, the work required for each subsequent step becomes progressively harder. The total energy stored is the sum of these millions of increasingly difficult steps. We visualize this accumulation using integration, plotting rising charge against rising potential. The total work done is the area of the triangle under this line. Integrating to our final charge Q stacks these tiny bits of work into one value. This area provides our first formula for stored energy, U equals Q squared divided by 2C. Depending on which variables we know, we can express this banked energy in three equivalent ways: 1/2 Q squared over C, 1/2 CV squared, or 1/2 Q times V. Because the electrostatic force is conservative, this energy is a fixed property of the final configuration, regardless of how fast charges move into place. Now that we have quantified this energy, we have to ask where it is physically located. We naturally look toward the charged particles on the metal surfaces, but our derivation suggests a broader volume. If we look past the solid metal and into the seemingly empty 3D gap separating the plates, the storage mechanism becomes clear. This gap has a measurable volume, defined by the area of the plates, A, and the distance between them, D. The empty space between the conductors is the actual storage vessel for the work we performed. To see why, substitute the geometric definition of capacitance, epsilon naught times area over distance. Next, replace potential difference, V, with the electric field, E, times distance, D. This gives the expression, energy equals 1/2 epsilon naught, E squared times area and distance. That final term, A times D, is exactly the volume of the space we just identified between the plates. This allows us to define energy density, which is the amount of energy stored per unit volume of space. By removing the volume term, we isolate the fundamental law. Energy density equals 1/2 epsilon naught times the electric field squared. This result is universal. It does not only apply to capacitors, but to any region of space containing an electric field. An electric field transforms a vacuum into a pressurized medium, physically holding the mechanical work that brought the charges into this configuration.